Hi, myself Naveen Kumar Saini in the course of antenna and wave propagation. Today we are going to discuss about the short electric dipole. So before going into the deep consideration or the concept of the short electric dipole, we will try to understand first of all what is the retarded potential which is time varying. So into this we are considering the antenna or the transmitting antenna at the time t, and the signal it will take time to reach at some distance. So we can see here, if we are assuming the concurrent conductor which is lying on the z axis, and the signal which is transmitted from this point, it is taking time to reach from this point to point P, right? So we can see R is the distance from origin, or you can say the origin or the point P, and the EM wave will travel with the speed of the light. So in that case, the current to reach at the point P can be measured as the retarded time, that is R t minus R upon C, right? So the current I can be written, which is written in the previous I is equal to Im sin omega t. So at the point P, this current will become this one. Okay, so this is a retarded current at the point P. So this retarded current occur because of the signal which will take time to reach from this point to from concurrent conductor to the point P, right? So another way of representing the wave equations in this case, that is the Ey is equal to sine omega t minus beta z. So we are considering the uniform plane wave which is traveling in the positive z direction. So Ey is equal to sine omega t minus beta z. So if we have the wave traveling in the negative z direction, so for this one, for this case, we will write the positive sign here, right? So Ey is equal to sine omega t minus beta z, which we are considering the positive z direction. In this beta is the phase shift, and whose value is omega upon c. So in this case, this equation will become Ey is equal to sine omega t minus omega r upon c sine omega t minus r upon c. So this is the retarded time which come into the picture when we are talking about the electric field in the y direction. So in this case, when you compare the equation third and fourth, then the equation 5 which we are getting, sine omega t minus r upon c is equal to sine omega t minus beta r. So retarded current will be equal to this much in the, when we write it in terms of the exponential. So I is equal to Im e की power j omega t minus r upon c, and so this is equivalent to omega t minus beta r. So retarded current density, which can be given as j is equal to jm e to the power j omega t minus beta r, right? Ampere per meter square. So magnetic vector potential, we can define it mu upon 4 pi j upon r dv is equal to mu upon 4 pi j upon r dv, right? So this is the equation which we come to know when we talk about the electromagnetic field theory. So we had taken this equation from that concept where the magnetic field come to the picture, and we wanted to calculate the magnetic vector potential, right? So this A is the magnetic vector potential. Okay, so now this, when we substitute the value of J from here to this one, then the magnetic vector potential in terms of the current density will become mu upon 4 pi volume integral jm e to the power j omega t minus beta omega, this will be beta r, right? Beta r divided by r. So this is the expression for the retarded vector potential because of the concept of r upon c is there. It come into the picture. So now come to the next important point which we want to consider, that is a short electric dipole. So short electric dipole is nothing but this is the linear antenna which is nothing but this is the which is the number of large number of short conductors which are connected in the series, which form the short electric dipoles. So this conductors or the short linear conductor which is known as the short dipole, or we call it as the Cartesian dipole as well. So as we know, when we have the two lines like this, two wires or the two transmission line or coaxial cable, so it cannot be transmit the signal into the air, into the free space. If we have the parallel lines, it cannot transmit the signal or the radiate the transmission, radiate the signals. So what we need to do? We have to do some flaring at this end, right? So we have to do some flaring at this end. So because of that reason, the antenna can transmit the signal. So another way of representing the same thing. So if we have this transmission line up to this point, so when we supply the signal, when we supply or give the feed to this transmission line, right? When we give a feed to this, so in that case the sinusoidal wave will occur, right? So at the positive sign and the negative sign. So in this case there is a matching between the maximum of this one and the minimum of this. So because of that reason the standing waves will occur, right? When the standing waves occur, so in that case the wave cannot be, or the radiation cannot be come out from the transmission line. So what we need to do? We will simply flare this parallel lines. We have the parallel lines, we flare it. So what happen? This is the pulse will come into this way. So at this edge, what will happen? One kind of the distribution will occur, right? So this distribution will occur. This is the current distribution. Okay. So this is the current distribution. This is because of the flaring of the terminal, the end terminal of the transmission line, right? So this is nothing but this is the antenna part. This is the antenna part from here to here. If we flare more, in that case what will happen? When we flare it more, so this will become like this one, right? So this is the maximum radiation which we will observe at the terminal end. So how this is occur? Because as we said, when we give supply to the from the source to this source terminal to the first terminal of the transmission line, so in this case the charges movement will occur between the conductor. So because of the oscillations of the charges, so at some instance of time this plate, when we are connecting at this terminal, so the positive charges are accumulated onto this, and at the bottom one the negative charges are accumulated onto this because of the movement of the charges or the oscillations of charges. So this is the equivalent circuit of this one, that this is the positive charges are accumulated onto this. So we are representing the plus Q charge. Negative charges are accumulated onto this terminal. So we call it as a minus negative charge cloud. So a distance between these two, this is the length L. Okay. So this is the equivalent circuit. This is the equivalent circuit of this dipole. So now say there is some case which we have to be consider. If L is the length of the dipole, which is very short as compared to the wavelength, that is the capital L is very much less than lambda, and the diameter of the dipole, so this diameter is also very much less than L. So we have to consider this case, and then we have the relation between the current and the charge, which is I is equal to dq upon dt. So these are the basics of the dipole which we are talking about. Now come to the point which where we want to find the what are the fields of the short dipole. So for this case, what we are taking? So we are taking this. This is the current carrying conductor or the dipole. Okay. So this is the case where we are taking this case, right? Current carrying conductor. So we want to find the electric field at this point P. So we are very much aware when we talk about the electric field. So we know the component of electric field is what? If we write it in terms of the spherical coordinate system, so it will be ER AR plus E theta plus E phi A phi. Okay. So E component in the spherical coordinate system will be ER AR, E theta, E phi, A phi. So ER will be in this direction, in the direction of AR. E theta is in this direction, in the direction of A theta, and A phi, which is a tangent So this is in the direction of A phi. We can write it as well. This is the direction of this one AR. This is the direction of A phi, and this one is the direction of A theta. Clear? So these are components which we have to calculate. So we have assumed already this dipole is lying on the z-axis. Okay, length is the capital L, small r is the distance from origin to the point P, theta is the angle, vertical angle, and phi is the horizontal angle in the spherical coordinate system, which we have already discussed in the previous lecture. Okay, so now let's start. So we know that the instantaneous propagation of current, which is given by I is equal to I naught e to the power j omega t, and retardation effect which occur into this, because then in that case the retarded current, which is representing in the square bracket of I. So in this case, this value of current will be here. Okay, if the current I is there, this one at point O, okay, at point O, then at point P, retarded value will be I naught e to the power j omega t minus r upon c. So along with this, we are just aware that magnetic vector potential, this is the magnetic vector potential. This is nothing but magnetic vector potential, which is in the direction of the current carrying conductor. So this is in the direction of AZ, or you can say in the direction of Z. So AZ is there. So it means this is along the direction of the current carrying conductor. So in this case, AX and AY will be equal to 0, right? AX is equal to AY is equal to 0. Okay. So when we put the value of, when we again solve it, in that case, okay. So for this diagram, we can understand first that R is the distance from origin to the point P. S is the distance from the element which we are considering here, from this point to point P. S1 is the upper edge, S1, and S2 is the lower edge of the dipole distance. So it means that this R is varying from S1 to S2, right? Okay. So if we consider that small r is very much greater than L, what is the meaning of this? If we are assuming in this case, this one and this one, so it is representing for the far field region. Okay, so this is the case of the far field region. It means the P point is very far away from the current carrying conductor. So that is why this small r is very much greater than the length of the conductor, or you can say the length of the dipole. So and the wavelength lambda is very much greater than lambda L, then the distance S of an element dz from the point P may be equivalent to the S. So this point S and R can be equivalent, can be same if P point is very far away. Okay, so in this case, this equation AZ will become mu naught upon 4 pi I, because I is a retarded current. Okay, and this length minus L by 2 to L by 2. So this is the nothing but the L by 2 minus L by 2, and this one is the L by 2. So dz is varying from minus L by 2 to L by 2. There is no point to consider about the current I here, right? So that is why this I, retarded current I, is going out from the integration. So only the dz will left, and the length of dz is L. So we can simply multiply with the L, right? So when we substitute this into the equation 2, so what will happen? The AZ will be equal to L I naught e to the power j omega t minus r upon c upon 4 pi r, right? So this is the equation which we are getting, which is the magnetic vector potential. So second, next point is the retarded potential V. So first is we have we found it out about the magnetic vector potential. Now we will talk about the scalar potential. Okay, so as we know about the when we talk about the magnetostatics, then there are two types of potentials are there. First one is the magnetic vector potential, second one is the scalar potential. Okay, so now right now we are talking about the scalar potential, that a retarded vector potential V of the charge distribution is given as V is equal to 1 upon 4 pi epsilon naught volume integral and rho upon s ds. So the solution for this one is rho naught e to the power j omega t minus s upon c, right? So this is the sum of modification to the equation or the diagram as well, that in the dipole what we are taking, we are taking this dipole from here, and this is the dipole whose length is L, and we are doing some manipulation to diagram. S1 is this distance, S2 is this distance. This is the case when the point of consideration is very far away from the dipole, right? So this point is very far away, so we can say this is the far field region. Again I am writing so that you can understand easily, far field region. So due to the far field region, these lines will look like the parallel lines, right? So S1, R and S2. So this distance, this is the theta, okay, and this length is L by 2 from this point to this point. So it means this is the theta and this is also theta. So this is also theta, then in that case this will be L by 2 cos theta. Similar to that, if we come to this point, so again this is theta, then this will also be theta, and this length from this point to this point is also again lambda length L by 2. So it is also L by 2 cos theta. So now we come to know about the what is the S1 and what is the S2. So in this case S1 we can see this is the S1 distance from this point to this point. So we can, what we can do, we can write it as the R minus this R minus L by 2 cos theta will be equal to S1, and here S2 will be nothing but R plus L by 2 cos theta, right? So from this diagram we can write the value of S1 and S2, okay? So before coming into this point, this was a case which we have to consider about this S1 and S2. So we are writing the scalar potential V, that is equal to, we know the formula for this, that V is equal to 1 upon 4 pi epsilon naught. We know that the V is equal to 1 upon 4 pi epsilon naught Q upon R. So we know this formula for the scalar potential. So we are writing this in terms for the in this case where this the positive charges which we are accumulated here, and here this is the negative charges accumulated here. So due to this point you can say we can say any of the point. Suppose this one is the point T, this one is the point you can say W, just for example. So at point T plus Q charges accumulated, at point W minus Q charges accumulated. So if we want to find the potential at the point P, so that in this case the potential at point P due to the plus Q charge will be 1 upon 4 pi epsilon naught Q upon S1, because S1 is the distance, right? Similar to that, the minus Q charge is accumulated, so it means the minus Q charge is accumulated, so the potential will be minus Q upon S2, right? 1 upon 4 pi epsilon naught minus Q upon S2. So when we combine, when we add the potentials at the point P, so minus sign will be there because of the negative charges accumulated, and the positive sign is there because of the positive charges accumulated at this point. I hope this point is clear to all of you, how we get this potential here. Now come back to the formula which we said about the I is equal to dq upon dt. So Q will be equal to I upon Q is equal to I into dt. So we can put this Q here. So when we put it, then Q is what? This is the I retarded current into dt. So we know that I naught e to the power I naught into e to the power j omega t minus s upon c, because this s is varying, as we said s is varying. So if we see back in this diagram, this s is varying from s1 to s2, okay? So s we are writing here. So s1 we know, s2 we know. So when we put the value of s1 and s2 into this equation, then the potential will be equal to this much, that v is equal to I naught upon 4 pi epsilon naught j omega and e to the power j omega t minus s1 upon c. So for this case s1 is there, and this for this case s2 is there. So we can write it and we can do some modification and simply mention convert in terms of the sine cosine forms, then the equation which we are getting like this. Okay, so after putting all the values of s1 and s2, we are getting this denominator. So this denominator is what? This is the r square minus L by 2 cos theta whole square, right? Okay. So this is equivalent to this much, right? So we are considering for the large distance, because we know that r is very much greater than L. So when the small r is very much greater than L, then this we can neglect this section. Okay, so what will left? Only r square will left here. Rest is same. Okay, r square is here and rest we are writing in the same way, right? Same thing is there. So next what we are doing, again we are doing some manipulation into that, so that these equations we are getting in terms of the cos and sine, right? So okay, so in this case the cos omega L cos theta upon 2c. So we are solving this equation, then we are come to this point. So again we are using this condition that lambda is very much greater than L. So when lambda is greater than L, so it means this value will be very small. When this value is small, then in that case cos theta, when it is very small, it will become the value of 1. Similarly, when this value, again we see, if we know that as we know that if sin theta is tan theta, that is equivalent to theta when theta is very small, when theta is very small, right? So this is equivalent to the theta, and when theta is very small, so it means cos theta. So in this case cos theta, when theta is very small, so this will be equal to 1, right? So that is why when we put all together, so in this case we are writing in place of cos, so this term will be there. In place of this, only this value will be come out, so this value will be 1, and in this value only this section will come out. So in this way, when do the same thing here, then which we are getting this equation. Potential is I naught L cos theta e to the power j omega t minus r upon c upon 4 pi epsilon naught c 1 upon r plus c upon j omega into 1 upon r square, right? Okay, so now come to the point, that is the electric field of the short dipole. So we know that when we have only static field, then in the static field we know that this relation, is equal to minus gradient of the potential. But when the short, we're talking about a short dipole, it means the current carrying conductor is there. So because of the current carrying conductor, the magnetic field potential will be there and the scalar potential will also be there. So which we have right now just derived, right? And if you want to calculate the magnetic field, then in that case here this is equal to mu H is equal to del cross A. Okay, so this is the same equation which we have already discussed in the magnetic scalar potential. B is equal to del cross A. So this is the mu H del cross A. Okay, so we are writing simply vector A, that is r AR plus theta A theta and phi A phi. This r is nothing but the unit vector. This is also the unit vector. This is also the unit vector. So we are doing some kind of manipulation into that, where we said the vector potential for dipole which has the in the z direction. So AZ is there. When the AZ is there, in that case AZ we have calculated, right? So by this AZ is in the direction of current carrying conductor. This is the AR in the outward world. This is the theta. So that is why the AR we are getting the AZ cos theta, and here AZ is in this direction, A theta is in this direction, and A theta will be equal to, with the minus sign, AZ sin theta with the minus. Okay, so AZ is given by the equations like this. So when we write it in the polar forms in the spherical coordinate system, then the gradient of the potential will be equal to this one. So these equations you have to take care. Okay, electric field we can write it as we said, and in that we know that E phi component is not there right now. So the AR will be ER plus A theta A phi. So A phi is 0. So del V upon del phi is 0, and the E phi is also 0. Okay. So when we put all together into this equation, when we put this equation into this one, so what will happen? We are getting in this way. Okay. So these are the equations which we are getting, ER and E theta. So ER and E theta is there, where the expressions are like 1 upon CR square. These are the these are the multiplication factor. Okay, these are the multiplication factor which is comprised the ER like this. So 1 upon C R square plus 1 upon j omega r cube, and this E theta j omega c square r plus 1 upon c r square plus 1 upon j omega r cube. Okay. Okay, so now second point is the magnetic field of the short dipole, which is simply representing H into this one. So again put the values of A by defining the spherical coordinate system del cross of A. When we put it like this, then A phi we are aware A phi is 0. So it means A phi is 0, this is gone. When the A phi is 0, it means the A del means A phi, that is 0, and del upon del phi, that is also 0. So it means del upon del phi is gone, and del upon del phi again gone, and A phi is 0. So this is also gone. So what will left? Only this factor will left. So in terms of the AR and A theta. So when we put all together, then in that case the H phi which we are getting like this equation. So HR and H theta will be 0. So for the far field, when we are talking about in this case, so what will happen for the far field? R is very much greater than L. So R is very much greater than L. So it means when R is very much greater than L, so we can see in the previous equation, when R is very much greater, so it means this factor will be 0. When R is very much greater than 1, in that case this factor will also be 0. Similarly, when the R is very much greater than very much large, so what it means? This is also 0, this is also 0. So it shows that ER will be equal to 0 in this case. But in this case, the E theta will be some factor of R will be there. Okay, so that is why they have mentioned that E theta and H phi, which we are talking about, the ER is not there, only the E theta and H phi will be there. Okay, so now come to the intrinsic impedance of the free space. So this is a very basic formula. We know about that E theta upon H phi is the intrinsic impedance, where E theta is this one and the H phi is this one. When we divide these two, then we will get the 377 ohm. So last is a radiation pattern. So radiation pattern we can calculate from the equation in this. When we find the E component, so in that case the maximum value will be, which we will observe when sin theta is maximum. When the sin theta is maximum, it means theta is 90 degree. Okay, so if this is a minimum value, so we can say E theta will be maximum when theta is 90 degree, and E theta minimum when theta is, you can say, very small or the 0, right? So when we put it all together, then at a 0 with null point we are getting, when the 90 maximum radiation is observed. So this is due to the dipole, because both the ways, both the direction the wave will propagate. So in this case, one dot net pattern which we are getting. So dot net shape which we will observe at this point 90 degree, 90 degree and 270 degree, and 0 degree and 180 degree we will observe the null points of the system. So I hope this point is clear to all of you, how we have calculated about the radiation pattern from the short dipole, right? Thank you very much.